This is the third section of the Trigonometric Identities and Equations chapter, and this is to do with trigonometric identities. Now the first thing is, what's an identity? Well, with an identity you'll see these three lines, like an equal sign, but with three lines in it. So what's the difference between that and an equal sign? Well, here's where we might use an equal sign. 5x minus 3 equals 17. Okay, and we'll get x equal to 4 if my maths is right. So this is true. This statement I've written here is true for when x equals 4. Okay, true for when x equals 4. For any other value of x, that statement isn't true. Yeah, you can put different values of x in, it doesn't balance. But with an identity, it's true for all values of x or whatever letter or variable we've got. So for example, if I had something like 6x minus 2, I could write an equivalent sign, and on this side I could write 3 and in brackets x minus well, let's try 2 outside the bracket rather than 3, and then in the brackets we would have 3x minus 1. Now the reason why I can put an equivalent sign there, okay, so this is what we call not an equal sign but an equivalent sign. I can put that there because this is true for all values of x. So it doesn't matter what value of x I put in there, that statement will be true. So that's the difference between equal and equivalence. So here we've got two statements. One, it says that for all values of theta, sine squared theta per cos squared theta is 1. And the other statement is that tan theta over is equivalent to sine theta over cos theta. So these statements are always true. It doesn't matter what angle you put in there, these statements are true. Now, if you'd like to know where they come from, you can watch this bit or you can skip it. Let's have a think about where this statement comes from. So here's an axis. Yeah, my x and y. Here. And I'm going to draw a circle on it. Like this. Perfect circle. And this circle is going to have a radius of 1. So these are 1 here. So it's got a radius of 1. And inside that circle, I could draw every single right angle triangle. So here's one. Here's an example of a right angle triangle that I can draw. And imagine that the hypotenuse of this right angle triangle here is the radius. So the hypotenuse of any right angle triangle I draw in that circle will equal the radius of the circle. Now I've got a formula for the for a circle, and that formula is, using the radius, x squared plus y squared is 1. Okay, and for this particular circle, because the radius is 1. So that would give the formula for the area of this circle. Now, if I think about the same thing, but using the hypotenuse instead, let's have a look at the lengths of each of these sides. I'm going to zoom in on this triangle here that I've drawn, which could be any triangle I've drawn inside that circle. Now, the hypotenuse of that triangle is 1 because it's the radius of the circle. Now, if I call this angle down here theta, then using simple trigonometry, I can work out what the lengths of the other two sides are. The length of the side at the bottom would just be cos theta, and the length of this side would be sine theta. Okay, you can use simple trigonometry to work that out. So what have I got? Well, I could instead call this the length of this side here. I could call it x instead because it's just the x coordinate. I could call the length of this side here y, because basically that's just going to be whatever that y coordinate is. Now, I've already got this equation, x squared plus y squared is 1. So instead of using x squared and x squared and y squared, I could instead use sine squared and cos squared, and that would be 1. Now the way that we write squared in trigonometry, so that there's like less confusion with the squared and we don't have to keep putting brackets in, is we would write it as sine, we put the squared there before the angle, and the same with the cos. So that's where we get this formula from. And then using the same triangle, this is the adjacent to the angle, this is the opposite to the angle. Yeah, so you could say that the tan of that angle is the opposite over the adjacent, y over x, or we could say the tan of that angle, instead of y over x, sine theta over cos theta. So we get that second identity, which is tan theta is equivalent to sine theta over cos theta. And we're going to be using these identities to help us solve different problems. Okay, so let's write the identities down. So tan theta is sine theta over cos theta. Okay, just a word that actually, although I've put theta here, it can be anything as long as these are all the same. So it might say, they all might say 2 theta, they all might say half theta, they all might say 45 degrees or pi or something like that. As long as they're all the same, the identity holds, and it's the same with this one. We've got sine squared theta plus cos squared theta is 1. It doesn't have to be theta there, as long as those things are the same. So as long as that and this are the same, that identity holds. Okay, and I suppose what we could do is, with this, we could take away sine theta or sine squared theta from both sides, and you'll end up with cos squared theta is equivalent to 1 minus sine squared theta. Or if we were to take away cos squared theta from both sides, we'd end up with sine squared theta is equivalent to 1 minus cos squared theta. So, you know, we can sort of play around with these identities and rearrange them how we like. So, for example, I could say here that tan theta times by cos theta is equivalent to sine theta. Yeah, so we can play around with these identities, do what we want with them. Okay, part A, we have sine squared 3 theta plus cos squared 3 theta. Now, because it says 3 theta, you might be tempted to think, oh, hang on, I haven't got an identity for that, but these are the same. That's what's important. And the bits I've highlighted in green, as long as those two things are the same, it could say 3 theta, 4 theta, anything you like, as long as they're the same, it's always going to be equivalent to 1. So that's the first one. Part B. So we've got 5 minus 5 sine squared theta. So the first thing I would do is I would factorize it to put the 5 outside of brackets. I could put equivalent there. So I've got 1 minus sine squared theta. Now if I have a look over here at the side, look, see, I've got 1 minus sine squared theta here. So I can change that to cos squared theta. So next thing would be it's equivalent to 5 cos squared theta. Okay, so that one is done. And then part C, I have sine 2 theta, looks a bit more complicated, over the square root of 1 minus sine squared theta, or 2 theta, sorry. And the top says 2 theta as well, so we can just apply the rules because they're all the same. Now the bottom, the bit under the square root would be cos squared 2 theta. Yeah, so we're using this identity here, 1 minus sine squared, or 1 minus sine squared 2 theta, we can change to cos squared 2 theta. So I would have sine 2 theta over the square root of cos squared theta 2 theta. Now obviously the square and the square root are going to cancel out, just leaving you with sine 2 theta over cos 2 theta. And then we can use the first identity, so that's going to be tan 2 theta. Might prove that that expression is 1 minus tan squared theta. Now here's a couple of tips. When you're doing proofs like this, you can start on the left hand side and see if you can make it look like the right hand side. You could start with the right hand side to make it, see if it looks like the left hand side, or you could start with both sides and try and make them meet somewhere in the middle like this. Okay, but my tip would be start with the most complex looking side, because it's much easier to start with something complex and simplify them. So, you know, it's not too much hard work to start with something that looks complicated and to simplify it. Yeah, that's not too bad to do. But trying to work the other way and start with something simple and trying to unsimplify it is harder. Yeah, that's harder to do. It's easier to simplify things than to unsimplify things. Right, so let's write this down. Let's start with the left hand side. That's the most complex looking side. Cos to the power 4 theta minus sine to the power 4 theta over cos squared theta. Now the top is like the difference of two squares, because you could think of the top as cos squared theta all squared minus sine squared theta all squared. So it's the difference of two squares, but those things are squared themselves. So when I factorize it, it will become cos squared minus sine squared in one bracket, and then cos squared plus sine squared. Yeah, so it's a little trick. So if it was like cos to the power 6 minus sine to the power 6, you can use the same trick again. It's actually the difference of two squares. You may not necessarily spot that straight away. Okay, so all of that is over cos squared. We'll leave it as cos squared for the moment. Might need to change it. Now, the cos squared plus sine squared here is 1, isn't it, basically? Yeah, that's one of the identities. So that will give us just cos squared theta minus sine squared theta, that's times by 1, over cos squared theta. And I can simplify this by splitting the fraction up. So I have cos squared theta over cos squared theta minus sine squared theta over cos squared theta. Now what will happen is the cos squared over cos squared will become 1, and the cos squared over sine squared over cos squared actually becomes tan squared. So that's a useful one to remember, because sine over cos is tan. Well, then what happens if you square both sides? Well, if you square both sides, you're going to get sine squared over cos squared, because you square the top and the bottom, is tan squared. Yeah, and the same would be if you cubed it or did to the power 4. And you could say in general that sine to the power n theta over cos to the power n theta is tan to the power n theta. Yeah, so that identity will be true for any power. So we have our final answer here. It just simplifies to 1 minus tan squared. Oh, actually it doesn't simplify to that. That's what we needed to prove. I've forgotten what the original question was. Here we go. We've proved it. And normally after a proof, you can write I've proved it, or you can write this here if you want to look it up, see what it means. Right. Here I've been given that in the first one, cos theta is negative 3/5 and its reflex. Find the value of sine theta. And a similar type of thing in the second question. It's asking for the exact value, and I presume this means exact value as well. Yeah. Right, so how do we do that? Well, my method is different from the book. I'm going to use a right angle triangle to find the size of my answer, and then I'm going to use a cast diagram, and we've come across those now. A cast diagram, I'm going to use that to find the sign of my answer. So is my answer positive or negative? So let me show you how this works. So I've got cos theta is negative 3/5 and theta is a reflex angle. Okay, so reflex means it's greater than 180. Yeah, their reflex angle is bigger than 180. So the first thing I'm going to do is to draw a right angle triangle here. I'm going to call one of the angles theta, and I'm told that cos theta is negative 3/5. Now I'm going to ignore the negative for a moment and just put that the sides are the adjacent over the hypotenuse 3/5. So if I use Pythagoras, it means that this side is 4. So I'll just use Pythagoras to do that. Okay, and that tells me that my answer, sine theta, well, I know that sine is the opposite over the hypotenuse, so that would be 4/5, but I now need to decide, is my answer positive or negative? So this is where I use a cast diagram. So 0, 90, 180, 270, CAST, and this is where this other bit of information comes in, where it says that the angle is a reflex, which means it's bigger than 180. It's down here. This is where the angle is. This is where theta is. It lives down here. Now I can see on that part of the cast diagram that sine would be negative. Anything down there is negative. The only place where sine is positive is up here when it's between 90 and 180, but theta isn't between 90 and 180, or it's not between 0 and 90. It'll be positive there as well. It lives down at the bottom, so it tells me that my answer is negative. So it's negative 4/5 is my answer. Okay, part B. This should be quicker. Now that we know the method, so sine alpha equals 2/5, and the angle alpha is obtuse. Okay, obtuse means that this angle is greater than 90 and less than 180, so we know where to put it on the cast diagram. So triangle first, like this. Let's call this angle alpha, and the sine is the opposite over the hypotenuse. So I'm going to use Pythagoras to work out this length here, and that will be the square root of 5 squared minus 2 squared, which is going to be 25 minus 4, which is root 21. So that's the exact length of this side here, root 21. We're going to keep it like that. We're not going to change it to a decimal. So what does that tell me? I'm trying to find cos alpha. So I found out that cos alpha, its value or its size is going to be the adjacent over the hypotenuse, root 21 over 5. Now I need to work out whether it's positive or negative. So cast diagram, C-A-S-T, like this. It tells me that alpha is obtuse. So if it's obtuse, it's in this part of the cast diagram. And the only thing that's positive in that part of the cast diagram is sine, which must mean that cos is negative. Any angle in that size, the answer will be negative. So the final answer, negative root 21 over 5, that's the exact value. So there's part A, there's part B. So we can use this triangle, right angle triangle, and a cast diagram to find these exact values. Right, given that P equals 3 cos theta and Q equals 2 sine theta, show that 4p squared plus 9q squared equals 36. Now this looks like we're going to be using this, sine squared theta plus cos squared theta is 1. Okay, so first thing we're going to do, since p equals 3 cos theta, then we've got that cos theta equals p over 3. And since we have q equals 2 sine theta, then sine theta equals q over 2. So now, using this identity here, we can write q over 2 all squared, that's like sine squared, plus p over 3 all squared, that's like cos squared, is equivalent to 1. So that's q squared over 4 plus p squared over 9. Let's multiply both sides by 4. So we get q squared plus 4p squared over 9 is 4. And then multiply both sides by 9. So we'll get 9q squared plus 4p squared is 36. And all they've done is they've just swapped it around so that you've got the 4p squared at the front plus the 9q squared is 36. So we've proved that statement to be true. Okay, you should now be able to do exercise 10C on pages 211 to 212. So just remember these identities. Tan of anything is equivalent to the sine of anything over the cos of anything. It doesn't have to be theta, it could be anything. Sine squared of anything plus cos squared of anything that's the same is equivalent to 1. When you want to find these exact values, then you can use this as an alternative method to the book, exact values. You can use your right angle triangle and a cast diagram to help you work out what these exact values are. And basically, your right angle triangle is going to give you the size, it will give you the fraction, and your cast diagram will give you the sign of the answer.